All right, so the schedule for today being the 11th, the homework for today is dealing with hypothesis testing, extending the process to the mean and to the standard deviation. And then today we're going to move a little bit further into this hypothesis testing area, talking about situations that come up, and then also the idea of the dual sample idea. Yeah, so we're getting down there because after today, then we'll have a test a week from today on Thursday. And then just another 2 more, and then we'll be all done. So yeah, we're past halfway point here. So that's fine. Then what's going to happen as far as the items that we do, depending on how things go, we might go a little bit further than what's on the homework, hopefully just to give you more of an idea of stuff that you might see, but you won't actually have to do, and that's all right. So we'll see how that goes. All right, but to start with, we need to try some review of hypothesis testing for the mean and for the standard deviation. So does anybody have any question about anything currently regarding that process? Okay, so we'll go ahead and make this happen then. When we have, let's say, we're talking about time in physical activity. For seniors. So we've got some kind of a home for seniors, and we want to say how much physical activity do they have, and we have some way to describe that. And so we're going to say that if we have a national number for the average of 25.3 minutes. And I suppose that would be that per day, maybe? Sure, we'll just say physical activity is they're out of bed and walking around. So for some kind of an elder care thing. And so we're going to do for let's say we're going to do Twin Cities survey. So we're going to survey a bunch of randomly selected seniors in the Twin Cities, and we find out that we have 100 people. And for this, we get a mean of 23.9 and standard deviation of 6.8. Now, if I were to give you this problem, what would you think is a reasonable claim to make here? From what I've given you, what thing would I try to prove based on this information? Abby?
You say, well, the null equals 25.3 minutes, and the alternative hypothesis would be less than 25.3 minutes.
Okay, and why would you say less than?
Because our survey that was conducted showed that it was less than the average.
Okay, so when we did our survey, this number came out to be less than the national number. So it seems reasonable that we would try to prove, is the population mean for the Twin Cities, is that less than this national number? So then, what symbols am I going to use for my null and alternative hypothesis here? Mariah, can you tell me what symbols I'm going to use for this?
Equals
Almost. I do have an equal sign and I do have 25.3, but that's not all I have here. Can somebody tell me what else I need?
Is it like a mu or the
I need mu, yes. I need mu equals this here. Okay, so when we talk about what is the null hypothesis, it's a statement about a measurement. And in this case, since we're talking about the mean, mu, the population mean, is what we're interested in. Okay. Tia, can you tell me what the next thing would be for the alternative?
Is that the same symbol?
It's the same symbol. What else?
Then isn't it the other way?
It's this way, less than
25.3.
25.3, yep. Now, this is something which is not obvious. This mu represents the population mean in the Twin Cities. This is not talking about the national number. The national number is where we got to 25.3. But the comparison that we are concerned about is, what about the Twin Cities? And I have the sample information, but that's not good enough. I want to find the population information about this. All right, so I'll give you a couple minutes, see if you can make this happen here. And we'll go with alpha of 0.05. Oh, I made a mistake. Right off the bat. I don't want this to be 100. I want this to be 1. All right, check with your neighbors, see if your neighbor's got the right stuff.
And this one is for the other one I can see, which is what I did. I Oh, here. Okay, so it's 19.05. Yeah, I don't know. Oh, because it's less. She's got 2.46. Then you're right.
All right, so we have stuff going on here, hopefully. We've got the hypotheses, we've got the claim. What two sheets of paper should everyone have in front of them right now? Steps for hypothesis testing and table F. All right. So, Alex, can you tell me the next step here?
I'm going to pass.
Okay. Liz Tomitz, can you tell me the next step here?
Are we supposed to like claim and not claim?
No, we did that. Okay. Maggie, can you tell me the next step here? Okay, Mariah, can you tell me the next step?
We just find the critical value first.
Okay, number one was the hypotheses and the claim. Number two is critical value. Yeah, that's right.
I got negative 1.729.
Negative 1.729. All right. Elena Miller, can you tell me what to do next? Okay, so what do you get for test value? Oh, okay.
How did you get that?
How did we get this? Mariah, how did we get this?
Well, we took the number 20, the total people in the survey, subtracted 1. That would be 19. So we look at our degrees of freedom under 19 and scroll over to 0.05.
Okay, so we have alpha and degrees of freedom is 19. That gives us that number. And since this is less than, it's a left tail test, that puts us over there. All right, Crystal, does that make sense?
Yes.
So, Mara, you got a number for your test value?
Well, I don't know if it's right, but negative 0.978.
That's correct. The test value is negative 0.978. So, yes, that's correct. So, Jessica, what do I do next?
Well, if you have the picture, you can go over there and draw that in, but
Okay.
it's not in the region, so we do not reject the one.
Okay, so this is where my negative 0.978 is. And I'm sorry, what did you say after that?
We do not reject the null.
We do not reject the null hypothesis then. All right. So, Elena Schmidt, what does that mean?
It means we don't have sufficient evidence to prove that our survey, the people that we surveyed.
Sorry, unfortunately, you're not correct. Okay. Tia, can you tell me what I say after do not reject?
No, I'm trying to figure out how you got the answer because my calculator still won't figure it out.
Okay, so you should have 23.9 minus 25.3 divided by 6.4 over the square root of 20. And you have to have the top part of the fraction separately from the bottom. So you can either figure each part separately or you can put parentheses. If you put parentheses around this and parentheses around that, then that should work. Or you can figure the top and then figure the bottom. That way. Did it work? Okay, good. All right. Hillary, can you tell me what I'm supposed to say after I do not reject the null hypothesis?
Not sufficient evidence to prove that the population came
Okay, so when we say, how do I express my conclusion? I do not express my conclusion based on the people that are in my survey. I express my conclusion based on the population mean of the place that I got the survey from. Elena, does that make sense?
Yes.
Okay. So when we say do not reject the null hypothesis, then we're saying that there is not, and maybe we put the word enough in there, there's not enough evidence to prove that the population mean of physical activity for seniors in the Twin Cities. But I'm going to take issue with one thing you said, Hillary. Physical activity for seniors in the Twin Cities is less than what? The national average. Because it is true that we were talking about a number, but the fact is that that number came from somewhere. So we put that in there. So what is this actually telling me? Is this true or is it not? Do seniors in the Twin Cities have less physical activity or do they not have less physical activity? Emily, what would you say to that question?
No decision.
No decision. I cannot tell. Even though my sample tells me it's less, it's not enough less, or it's not substantially less to prove for a fact or with amount of confidence that it's true. I don't have enough evidence here. Now the situation is, if I were to survey more people, that would help me. That would make my answers more accurate. But I don't know that I would get the same answer, right? Because if I measure 100 people instead, the number is going to be different than this one, and the standard deviation is going to be different. So there's going to be a lot of different things about the situation if I just measure more people. If I think that I'm going to get the same kind of results, then it might make sense for me to talk to 100 people instead of just 20 people. Then maybe I'll get more of an idea of what's actually going on. But currently, with these 20 people, this is not enough evidence to prove it. But it's not just that it's 20 people. The standard deviation also affects that. That's here on the bottom. So the standard deviation and the sample size are going to change my answers. And if I ask 100 people, then everything about this is going to change. All right, now, what I'm going to tell you then is what the confidence interval would be for this. If I were doing a confidence interval, then that interval would be from 21 to 27. So based on this thing, the mean was about 24. The confidence interval is 21 to 27. Is that less than 25? The answer is
still within the range.
if I ask the question, is this thing here less than 25? Then actually I don't know. It could be less or it could be more. So I still can't answer the question. The actual mean, the population mean could be 26 or 26 and a half, or it could be 21 and a half, I don't know. So based on this confidence interval, I'm not able to answer the question, is it less than 25? I don't know. Now, pardon me. I do want you to see, at least, how this would work on a spreadsheet. Because, pardon me, given the fact that when you look at something that's out there in research land or whatever, that you're going to have the ability to not just put things in, but you're able to have a spreadsheet where the different formulas are already set up. Or you can set them up yourself once you know how to do spreadsheets and formulas. But what I have right here, and you can't necessarily see it, but maybe if I set equal t dot dist. If I put in here t distribution, t dot dist, then I can put my t value, my test value in here. I put in my degrees of freedom and I put in my cumulative. And it will give me almost like alpha of 0.17. So then that's not really good. I will come back to this, but I want to show you what would happen if I changed this sample size to 100. If I change the sample size to 100, my test value will change and my critical value will change. If you look on your sheet for table F, there is a place where it has the degrees of freedom of 100, where technically you would have to have 101 here, but it's the same number, 1.6. But if you put 100 in the bottom of this fraction, you take the square root of that, it changes your test value to be this number. So then we would reject the null hypothesis. So again, what I want to show you is what we're doing with the table and everything like that. Computers are able to do it with no problem. And they can look up all kinds of degrees of freedom, not just what we have on the table. So it's not really necessary for us to say, well, what about all the different possibilities? As long as you can read what's on the table, then hopefully you'd be able to figure out how to do it on a computer so that if somebody said, can you do this research, you could. Generally, what happens for most people, they're not actually doing the research, but they have to look at what somebody else did and see if it actually works. But at least you can see how that would happen. But certainly, if you want to be good enough to do research in your field, then that means that you become more employable, right? And you can even aspire to higher things like management. So I don't want you to think that I want you to stop right where you are. You can move on and you can actually get good at research or whatever. All right, so what we've done right here is a one-tailed test. How would we have it different if it was a two-tailed test? What would that look like? First of all, it would be phrased in a different way. Instead of having this idea of less than, we would have something right here which would be not equal to. And so then sometimes they say it like this. Is Twin Cities mean different from the national? So they use this phrase different from, and that means not equal to. And the concept here is starting out before you do the survey, you don't know whether it's going to be less than or greater than. And so then you say, I'm going to set it up so it could be less than or it could be greater than, either way. And then you set up the problem, and then you actually go out and do the survey. Again, I don't agree with that. I think it's more reasonable to do this. But the two-tailed, again, you would be looking up your critical values using the two-tailed thing, right? So then if it's two-tailed, what number do I get from table F if degrees of freedom is 19 and I want a two-tailed alpha of 0.05?
2.093.
19, two-tailed 0.05 is 2.093. Right? Okay. So what does that mean? That means negative 2.093 and also positive 2.093. So it could be in either section because it's two-tailed. Now, hopefully you can see in this particular situation, it wouldn't change our answer at all. But you can see maybe in some situations it would. Yeah, and you know, there are situations where two-tailed tests are more common, like traditional statistics says you have to do a two-tailed test. Okay, well, all right, I will. I have to. But that's how it's set up. All right. Now, the next thing that I want to consider is how most research is described. When you get to the end of a research thing, most of the time they don't actually go through and do the conclusion. I'll tell you why. Let's go back to our percentages. So let's say we're doing infants. And so I've got infants, and we're talking about let's say that they have, they test positive for what kind of thing did they test positive for?
Influenza.
Hmm?
Influenza.
Ah, good. And so let's say that if we're going to ask how many infants get influenza, let's say 7%. So, national number is 7%. And we're going to do a sample of 200 infants. And we've got let's say it's 10%. Okay, so I've got my null hypothesis is that P is equal to 0.07. my alternative hypothesis would be that p is greater than 0.7. But if you look at your steps for hypothesis testing, we are not going to use the traditional method. We're going to use the p-value method. So if you're looking at that, we've stated the hypotheses. We have identified the claim. The question is, let's say that these are from Mayo. And so then we say, is the population proportion at Mayo higher than the national? Okay? So, with this, the second step is to compute the test value. So let's just see if you can make that happen. I want you to compute the test value for this situation here. We don't. What I want right now is the test value. Caitlin, you got a number? Okay. Casey, got a number?
I do not.
Okay. Emily, you got a number?
No, are we using the z equals p hat minus p over the square root of pq divided by n?
Yes.
I was doing a little bit.
Okay.
Should be 1.663.
1.663 is the test value. All right, any other questions about this so far? Oh. Sure. Can you tell me what the formula is?
She said earlier, P hat something, P hat.
Okay. If you don't know the formula and you don't have it in front of you, that's a bad situation. Okay? So if I'm going to go through this for you, then I'm going to tell you what the formula is when she had it in front of her. If you have it in front of you now, then now I need to know what numbers to put in. right? What's p hat in this situation? What does p hat stand for? What's the meaning of that?
Sample proportion.
It's the sample proportion. So if I look at all these numbers here and I say, where's the sample proportion? The national number is 7%, the sample number is 10%. So this is the sample, this is the test. So then I'm going to do 0.10 minus, well, what's P? Where do I get that from? I get that from the null hypothesis, 2.07. So that goes here. Now, what I just did for you is I told you where the numbers went into the formula. That's really important. But it's also really important that you can actually put these numbers into your calculator to get the right answer. And it's also important that you would be able to do that separately, if I'd say that. So that you would say, all right, I'm going to look at the problem, I'm going to know where the numbers go. And I can put in my calculator. So both of those things are important. All right, any other question about this test value? Okay. The next thing it says is to find the p-value. This is step number 3 on the p-value method. What is the p-value? The p-value is alpha as a variable. Most of the time, when we start a problem, we are told what alpha is, or we decide what it is. But it is also true that we can treat the concept of alpha as being something that changes based on the situation that we have. So what I'm looking at right here is I'm going to use this information, I'm going to come up with a number, and that's going to mean the same thing as alpha. So the question is, what does alpha mean? What's the meaning of the symbol alpha? Abby, can you tell me the meaning of the symbol alpha? Not quite. Yinan, can you tell me the meaning of the symbol alpha?
Yeah.
Okay. Mattia, can you tell me the meaning of the symbol alpha? Okay. Lena Schmidt, can you tell me the name or the symbol alpha?
I cannot.
Okay. So, anybody got an idea, Hunter?
It's expressive proportion.
No. Alpha.
Chance of being wrong.
Alpha is the chance of being wrong. Okay. So when we say, what does alpha actually mean? It is my chance of being wrong. So the p-value is our chance of being wrong, but the p-value changes. Whereas alpha is set to be only certain numbers, right? 0.1, 0.5, or 10%. So now what we're going to consider is that every problem that we do is going to create a p-value, which is going to tell us how likely it is that we are wrong. Now there's a longer definition of this, okay, and I'm going to give it to you, but I'm not going to expect you to remember. Okay, the p-value. This is the chance of a random occurrence assuming H sub 0. So if H0 were true, in other words, in this situation, if it is true that 7% of infants have the flu, what are the chances that randomly it comes out to be 10%? Or higher. Okay? So this is what it looks like. I'm going to use this test value, 1.663, and I want to find the area of the tail. The area of the tail is the same thing as the p-value. So as I described, it is the chance of having a random occurrence away from the mean, assuming that the mean or the middle number is 0.07. So if I assume that the true value is 0.07, what are the chances that I could be out here at 0.10? That's that area. Well, how am I going to find that? How am I going to find the area of the tail if I have my z-score of 1.66? Anybody have any ideas of where I would find that information? I have a z-score of 1.66 and I want to find the area which is to the right of that. Where would I look? Table E, yes. So not table F and not table G, but table E. So that means I got to get my table E, which is hiding somewhere. Here we are, not, yes, here we are, table E. How do I find that number?
You find 1.6 and then take that over to 0.06.
Well, that will help me, but it won't quite give me what I want. What number do you find when you go out there, Jessica?
0.9515.
0.9515. Is that the area of the tail?
No, you subtract 1 from it.
I would subtract it from 1, technically, yes. What happens if I subtract that number from 1? What do I get?
.0485.
So the p-value here is equal to 0.0485. Jessica, what is your opinion of that p-value? Is it
not in the area?
Okay, that's not what I'm asking. That number, 0.0485, would you consider that that would be an unusual event?
No.
Well, you had a 50-50 chance.
Well,
Okay, Sierra, how do we know if it's an unusual event?
it's below 5%.
Is it below 5%? Yes, it is. So we would consider that this would be an unusual situation for me to be wrong. So if it's unusual for me to be wrong, what does that mean? I can be right. Okay, so what's the situation? I want my chance of being wrong to be a low number. I want a low number. Specifically, I want it to be less than alpha. So I have a number here, which is a probability. It's my chance of being wrong. and it's a low number, is it lower than alpha? Well, if I pick alpha of 0.05, then that's, oops. So if I say alpha is equal to 0.05, the p-value is less than alpha. Step number 4, make the decision. If the p-value is less than alpha, then reject the null hypothesis. Once again, understanding the process is good, but understanding the meaning is also good, all right? The p-value is my chance of being wrong. I want that to be small. I want a small p-value. Right now, I have a p-value of 0.0485. Is it less than alpha? Well, if alpha is 0.05, then yes, it's less than alpha. So that means it would be unusual for me to be wrong. So that means I might be right, that my claim has evidence. So I'm going to reject the null hypothesis. So then I say there is evidence to prove the alternative.
Would we always assume that the alpha is supposed to be 0.05 then?
If it's not actually given to us before the problem starts, yes, we would.
Okay.
But if, in this situation, if the problem here, so we're just going to go through another one of these p-value things so you know how they work, and hopefully make everything happen. So let's say that we've got a situation of might as well keep something going on here, but let's just say infants that the proportion being tested for an infant. So not every child out there gets tested, right? But let's say that this national number was, 35%. And let's say that a sample of 300 that we had observed a 28%. So is the population proportion at Mayo now lower, right? Okay. All right, so let's see if you can make this happen. I've given you the numbers. I want to see if you can figure out using the p-value method now. See if you can draw the right conclusion. That's weird. Oh, yeah. Oh, I better say that, shouldn't I? Okay. All right. Okay, check your neighbor. See what your neighbor has going on.
Is it 0.5? Is he still wanting us to use 0.5?
Oh, I don't know, I just told them.
Yeah. Right, okay. So he wants us to.
All right.
Which would give us.
Okay, Lynn, can you tell me what my null and alternate hypotheses are? T is equal to 0.35, T is less than 0.35, okay? So we got that part. First step, null and alternative hypotheses. Compute the test value. Mattia, you got the test value? Okay, what do you have? Yeah, negative 2.54 is our test value. Okay. So, Casey, can you tell me what I want to do with that number?
Well, for the next step, I'm gonna go into table E,
Okay.
and you wanna find negative 2.54.
Okay.
And you get 0.0055.
So, Casey, do I take 1 minus that number?
No,
Why not?
because it's already skewed to the left.
It's already to the left. That's correct. Now, this is where things get a little dicey. Melissa, can you tell me what I need to do next? Okay. So technically, you're right. The next thing to do is pass. Okay. All right. Yep. That's okay. Mara, can you tell me what to do next? Okay. Liz Tomitz, can you tell me what to do next?
Pass.
All right. Somebody tell me what to do next. Make the decision. Good. That's right.
Don't you reject it because it's less than alpha?
technically your answer is correct. Unfortunately, it's not completely correct. Okay? What does the word it stand for? I'm going to reject what? The null hypothesis. Okay, we don't use the word it.
I put HO on here.
Yeah, okay, so yeah, read your stuff and you're gonna be great. So, the p-value is the area of the tail. And in this case, the p-value is 0.0055. I want a low number. I want it to be less than alpha. If alpha is 0.05, then the p-value is less than alpha, so I will reject the null hypothesis. So what does that mean when I reject the null hypothesis? Maggie, can you tell me what that means when I reject the null hypothesis? Okay. Mariah, can you tell me what it means when I reject the null hypothesis?
Pass.
Katie, Larkin, can you tell me what it means when I reject the null hypothesis?
Pass.
All right. What does it mean when I reject the null hypothesis? There is evidence for what?
To prove the population proportion in Mayo is greater than the national average.
H1. Okay? There is evidence to prove the alternative hypothesis, not the null hypothesis. Right, Melissa? And the alternative hypothesis, Jessica, was what?
No, oh, you want me to just restate what it's saying?
Yeah, tell me what that is.
Well, I put is enough evidence to prove the population proportion at Mayo is greater than the national average, so then
Less than.
less than. So
Okay, the previous problem was greater than, this problem is less than, okay? So what we're proving is that the population proportion here at Mayo for testing for influenza is lower than the national. And there is evidence to say that that's true. Okay, question.
I guess I'm confused about when we're supposed to subtract the p-value from 1.
Okay, if it's a left-tailed test, then our table gives us the number directly because the table's numbers are to the left. If this had been a right-tailed test, greater than over here, then if we look at the table, that would give us this big number, but we don't want that. We want the tail here on the right, so we subtract from 1.
Okay, thank you.
Okay. That's a good question. Okay. Any other questions about this process so far? What this means to us right now is that a p-value of 0.055 seems to be kind of impressive because it looks to us like there's definite evidence here. This is not just a random fluctuation. This is, hopefully, clearly a difference. There is a real difference here between what we have, the 35 or the 25% versus the 35. There's a substantial amount of difference here. The problem is we are assuming that this national number applies to Mayo. It might not, okay? There might be some reason why that it would be crazy for us to apply this national number to the situation. There might be something very substantially unusual or different about Mayo compared to any other place, but I assumed that it was the same as the national number. In a sense, logically, it doesn't make sense for me to do that. It doesn't make sense for me to say that if I have a national number that it definitely applies to everybody. So then a lot of people don't like the p-value because the p-value is kind of forcing us to say these situations are the same when they might not be the same. Whereas with the confidence interval, when I have my confidence interval for this, which turns out to be between 23 and 33%, then I say, okay, I got 28. It's actually between 23 and 33. This is more information. This is saying it doesn't matter to me what the national number is. It doesn't matter to me what anything else is. All I'm saying is this is my confidence. And I know that's where my population proportion is going to be. Now, if you want to compare it to the national, you would say, well, it looks pretty clear that it is less than the national. But I'm not assuming anything before I calculate my confidence interval. And there's more information. Here, it just says, oh, it's less than. 28 is less than 35. But now I actually know where the real or the population number is, 23 to 33. So once again, confidence intervals are generally seen to be more information. All right. All right, so far. So far. Okay. Now, the next thing that we need to do is to expand our world a little bit. And we're going to talk about two sample comparisons. When we did hypothesis testing at the very beginning, what did we say the purpose was for hypothesis testing? The purpose for hypothesis testing is what? It's to prove a difference. Previously, we had to have some kind of a number that was given to us as a standard number. And a lot of times we had a national survey that we wanted to prove. But now we're going to say, I have two different populations. And what I want to do is to prove a difference between those two groups. Specifically, we're going to work with proportions. So I'm going to prove a difference between two population proportions. Now, hopefully you can see that this is very important for us because it's not just, do I have some standard number that's out there, but I'm actually saying, for example, if I give these people medicine and I don't give these people medicine, how do they differ, right? So then you're saying I have maybe my control group and then I have my other group. I'm going to measure the proportions and I'm going to see if it makes a difference. But I'm taking into account that even for my control group, there's variation, right? So there's variation in the first group and there's variation in the second group. So I have to consider both of them as being numbers that change. So then, hopefully, based on statistics, we can actually make this work, okay? So let's say, for example, that I'm going to measure, let's say, percent of people who recently visited. We'll go to someplace that people visit. Let's just say a city park. Let's just say in the past month. And so we're interested, how often does this happen? And let's say in La Crosse, it was 300 out of 500. And let's say on Alaska, it was 312 out of 600. Well, what happens here? We're going to use traditional method, all right? So we have to start by saying what are the hypotheses, okay? And so now, instead of using just the letter P to stand for proportion, we have to recognize that we're comparing two different population proportions. So what we're going to do is we're going to decide that one of them is the first one and the other one is the second one. It doesn't matter which one we choose, as long as we're consistent. So we're going to take this here, this information for La Crosse, and we're going to, based on this, say X1 is 300, N1 is 500. That's going to be La Crosse. And then on Alaska, X2 is 312, N2 is 600. So it's important to kind of keep track of what you have in terms of the numbers and what they look like. And we do need all these numbers. Okay? So then, we are going to be comparing proportions. Let's find out what P hat is for both of these. So what's P hat 1? I'm sorry? 0.6. What's P hat 2? 0.52. So we take x divided by n, that gives us our P hat. So again, what I'm going to do here is I'm going to look at these results and I'm going to say it makes sense for me to do my hypothesis based on these numbers. So my null hypothesis will be P1 is equal to P2. And the alternative hypothesis is P1 is greater than P2. So it seems reasonable here. If I did my survey and more people in La Crosse have visited the city park, then I'm going to try to prove, is the population number in La Crosse higher than on Alaska? Now, if in your textbook, if it says different from, are these different from each other, then that would be a two-tailed test. But here, I'm going to assume that it's a one-tailed test and La Crosse would be higher than on Alaska. And certainly on a test, I'd make that clear. So what we're looking at here is we're saying I want to prove a difference between these two population numbers when all I have are sample numbers. Well, what's next? What do I need next? What comes after stating the hypothesis and identifying the claim? Find the critical value, actually. And let's use alpha 0.05. Where do I look for this when I'm using proportions? Emily, can you tell me?
Table F,
Table F? Where on table F?
in the one tail alpha 0.05 all the way at the bottom.
That's correct.
1.645.
All right. So yes, I'm using table F and I'm using z-scores. So I go all the way down to the bottom. This is 1.645 right here. That's my critical. And there's my rejection region. Now technically, I could have done the test value first and then done this. Doesn't matter. But this is what that is. Critical value, rejection region. Now I need the test value. It looks like this. The z-test for comparing. Okay, now if you have the formula written down, then we're going to talk about what's in here, okay? First of all, we have p hat 1 and p hat 2. We find those by doing x1 divided by x2 and 1 divided by n2. That's what we have over here, which we already did in this problem, so we know what these numbers are. That's p1 hat versus minus p2 hat. But then we have this, p1 minus p2. P1 minus P2 actually is not necessary for us because we assumed that P1 was equal to P2 at the end. So this section of the formula is actually just 0. So we don't really need it. And that's generally true. We're assuming that the two groups are the same. And so then P1 and P2, which come from the null hypothesis, Even though we don't know what they are, we're assuming that this subtraction will come out to be 0. So what I currently have here is 0.6 minus 0.52. That's what's on top of this fraction right now. I don't need the other thing. But what else do I need? I need P bar and Q bar. And P bar is where I add the X values on top, add the N values on the bottom, and divide. So in this case, P bar is going to be 300 plus 312 divided by 500 plus 60. And what we're going to do is we're going to go out to 4 decimal places for this, just to make sure that we have enough stuff going on. But it probably would not make too much difference if we went out to 5 or 6, but definitely 4 is necessary. We have to have at least 4. So what do we got for a number there then? 0.5564 is that number. And then Q bar would just be 1 minus P bar. So that's 4436. So then what do we want inside this square root? I want 0.5564 times 0.4436 multiplied by 1 over 500 plus 1 over 600. The best option for doing this problem is to use your calculator and not write down any intermediate steps, but just have the bottom part of the fraction. So on your calculator, it would be good to use parentheses if you have them, so that you would say square root parenthesis 5564 times 0.4436 times another left parenthesis 1 over 500 plus 1 over 600 right parenthesis equals, and you would get that number on the bottom of that fraction. And we're going to take that number to 4 decimal places. So, Melina Schmidt, do you have that number?
I have 2.659.
Okay. I think that'll work for us. 2.6593, you said? Okay. Now, that is going to depend on how much rounding off you do. If you round off everything to 4 decimal places, then it might be a little bit different from this. Okay. If I just go with this, yeah. So if I round it off to 4 decimal places, this number is a little bit different. It's going to be 2.6578. So using the calculator, gives you the ability to not have to worry about writing stuff down. If you try to go through this bottom section step by step, more than likely you'll make a mistake because there's just so many numbers. But if you allow your calculator to do it, then it's possible you can actually get something close to the right answer. And it's not actually necessary to round off if you can keep the numbers in your calculator. There is something on most calculators called an answer button, ANS. So then it would be possible for you to do the bottom of this fraction and then just take the top part in parentheses divided by answer, and it'll bring that whole number back. You don't have to round off.
I don't get that answer right either, Liz.
Okay, what did you get from the bottom of the fraction?
Well, when I did it all through the calculator, I got .0018.
You probably didn't square root.
Well, that's what I started with. I started by doing the square root, and then in the first parentheses, I did 0.5564 times 0.4436, and then ended the parentheses.
Okay, you can't do that. When you do square root and you put a left parenthesis, you can't put that right parenthesis until you get this part. So you have this times 4436, and then times, and then another set of parentheses.
Okay, so don't close.
1 over 500 plus 1 over 600, and then close it twice. Now, if your calculator doesn't have good setup for parentheses, then you have to work from the inside out. You'd have to do the thing with the 1 over 500, 1 over 600, multiply by the other one, multiply by that one, then take the square root, and then write that number down. But hopefully, if your calculator is set up to do this square root and then parentheses, then you'll be in good shape. So Jessica, does that work? Okay. Okie doke. So then, pardon me, my test value is basically 2.66. It doesn't affect it to have out to this many places, because when we're comparing it, we're only going out to 1.645. Clearly, it doesn't matter which number we use to say, is it out there or is it not out there? Okay. So, Mara, can you tell me what I'm supposed to do next? Okay. Katie Larkin, can you tell me what I'm supposed to do next?
With like this equation here, or what are we?
Okay, I did my test value.
Okay,
It came out to be 2.66.
okay. Then just don't you have to decide, or do you have to do p-value?
We're not doing p-value, we're just using traditional method here. Okay.
So you just have to like decide if you're gonna reject it.
Okay, you used the word it, which is bad.
Reject the null hypothesis.
Okay, so yes, we're going to decide whether to reject the null hypothesis.
Yeah.
Okay, so Katie, what should we do here?
I don't know.
Okay, Mariah, can you tell me what I'm supposed to do here?
Do not reject it.
How would you make that decision?
If it's not the rejection region.
Okay, that would be true if it were not in the rejection region, but the question is it or isn't it?
I don't believe so.
Okay, and how would you know, other than by simply guessing?
Because it just seems a little.
Oh, okay, seams, all right, we're not gonna do the seams, okay? So Liz Thomas, can you tell me what I need to do next?
Look at the picture.
I look at the picture, what does the picture tell me?
I can't see the rest of it. It's in the rejection zone.
2.66 is in the rejection region because it's out here. So what does that tell me, Liz? No. You use the word it again.
Reject the null hypothesis.
That's correct. We're going to reject the null hypothesis. And eventually, after weeks and weeks of me saying it, you won't say it anymore. When I say what, then you will say, oh, that's right, reject the null hypothesis. Okay. So now we've rejected the null hypothesis. Minan, can you tell me what that means?
There is evidence to prove that there is evidence as well.
Okay, that's the first thing. There is evidence. That's right. That's good. That's what we want. Okay, Melissa, can you tell me what else I need to write? There is evidence. What?
Is a difference between when people like go to parks and cross in Alaska.
Okay, you're getting there. You're almost there. Emily?
There is evidence that the percent of people who recently visited city parks in La Crosse is greater than the percent of people who recently visited city parks in Alaska.
Okay, so it's not simply that there is a difference, but that La Crosse is greater than on Alaska. And that the population proportion, I don't know if you use those words, but the population proportion of park visitors, recent park visitors in La Crosse is more than Alaska. Once again, the samples told us that the numbers were different, 60% versus 52%. However, those samples are not enough. We want to find out, is it true for everybody in La Crosse and everybody in Onalaska that the proportion would be higher when we compare the two? So hopefully, if we did this correctly, these are randomly generated samples of everyone in those two communities. And so then we are able to make this decision that the difference here is a real and what we might call statistically significant. So we would say, it looks like Onalaska visits their parks more often than the Onalaska people when we're looking at just how many proportionate in the past month.
You mean La Crosse versus Alaska?
La Crosse is fine. Yeah, I should, well, whatever I said, I meant to say it correctly, no matter what I said. Okay, so La Crosse proportion is higher than Alaska proportion for the population, not just for the samples. Now, having this information in mind, okay, might be relatively good, but then we ask the question, does Melissa have her hand up? The answer is yes. Okay.
So is it safe to say when we're summarizing our results
Yes.
that if we turn what is in the alternate
Yes.
hypothesis into like words,
That's right. That's what will
That's-
give you the answer.
okay.
Yes. Yep. So the alternative hypothesis is the thing that we are trying to prove. And so when we say there is evidence for the alternative hypothesis, when we put it into words, that's what we want. And again, these are population proportions from these two different things. Yes.
Okay, and then if, for whatever reason,
Right.
Test value is not in the rejection code,
Right.
not reject the null hypothesis.
Right.
So you would say that there's A, no decision, and then there is not enough evidence that the population proportion of Racing Park visitors in La Crosse is more than otherwise.
Correct. So there's not enough evidence to prove the alternative hypothesis. Once again, that's what the information is, but there's not enough evidence to prove it. Okay? Even though the samples are different, there's not enough of a difference to prove what's going on. Okay. All right. 3 things I want you to understand now based on this. The first one is that there is a difference between statistical significance and practical significance. Here I have a difference of 60% versus 52%. Does that actually make a difference in how I run my parks or anything like that? I don't know the answer to that question because I don't run parks. But it would seem like that's not a huge difference, 60 versus 52. Maybe it is. But if I had a big enough sample size, I could prove there was a difference between 60 and 59 if I did 10,000 people or something like that. But that doesn't mean it's real. It just means that I just proved something. So whenever we're looking at these things and we say, is it of practical significance? We have to have some experience with the situation to know whether it is or isn't. Here, we found these numbers and they are different. But I don't know that it matters to the parks people because I'm not a parks person. Okay, the second thing is, we could have used the p-value method for this instead of using the traditional method. What would happen if we used the p-value method? We would have just looked at this 2.66 and asked the question, what is the tail? If I see a 2.66 out here, what is my tail going to be? How would I find that tail? All right, you got anything?
Be 0.9961.
Okay, 0.9961 would be the area to the left. Which I don't. I want the tail. Now there's one easy way to find that, and that would be to look at negative 2.66, because then that would be on the other side, and we know that it's the same on the other side. Or we could take 1 minus 9961, either way. And we would find that this is 0039. Liz Tomitz, can you tell me what would happen in my p-value when I do that? Okay. Elena Schmidt, can you tell me what happens when I find this p-value of 0039? Okay. Who can tell me what to do with that p-value?
You would reject it.
No.
No.
You use the word it.
I'm sorry. You would reject the null hypothesis because since it wasn't stated, we're assuming that the alpha was 0.05, and this would be less than that.
Okay, the p-value is less than alpha.
Yes.
So we would reject the null hypothesis. Yes. So this is our chance of being wrong, which is very small. So we're saying these are not just randomly different from each other. There's an actual real population difference between Onalaska and La Crosse because of the sample sizes and the differences and everything else. So the other thing that happens here is that we could create a confidence interval for the difference between the proportions. And it looks like this. Now, as fun and interesting as this might be, we're not going to worry about it. Okay, so this is a thing where we would say, okay, what is the confidence interval for that difference between those proportions? And it comes out to be, it looks like this. P1 minus P2 is somewhere between 2% and 14%. So if we say, is lacrosse, do they have a higher rate of going to the park than Onalaska does? We would say yes. Well, how much difference is there? Somewhere between 2 to 14%. So what I have right here, this is 12%, but the actual difference could be as low as 2%, which is really nothing. So even though I said this is statistically significant, the fact of the matter is I don't know how significant it is. It could be anywhere from 2% to 14%. It's crazy, right? So I'm going to show you a research study that was done here for influenza vaccination coverage and effectiveness in young children in Thailand, 2011 to 2013. And if I look up the words p-value, you see how they are all highlighted here. And the little C1 symbol here, this is actually a decimal point. I don't know why it came out that way, but it's talking about how many healthy children received the vaccine versus how many at-risk children received it. And in 2 different years, they were different. But it doesn't say anything about why or what matters. It just says, hey, look, we found numbers and they're different from each other. Great. I don't know if they later on describe exactly what it means. But this, I thought, was very interesting. Here is your vaccine effectiveness. This vaccine was found to be 55% effective. But the confidence interval is everywhere from -72 to 88. So if you find that this is, oh, look, it's 55% effective. But what is it really? Could be anywhere from bad to really good. You just don't know. This one over here is from 13% to 85% effective. Well, if something's 85% effective, raw, that's really great. But it could be as low as 13. So when you say, how effective is that vaccine? 64. No, that's not correct. How effective is this vaccine? Somewhere between 13 and 85. That's the truth about the effectiveness of this vaccine. This 64 is not a true number because it's just a sample. It doesn't represent the actual effectiveness. And this one over here is crazy. Because if you say to somebody, oh, it's 55% effective, they say, oh, that's pretty decent. Except it could be 72% not effective. So this is just an example of how in an actual research study, when you do confidence intervals, you can actually see what's going on and you can see what doesn't matter, right? Or what they didn't prove. So you have to be really careful about what numbers you're going to take to mean what they mean based on this kind of stuff. All right, that's good enough for today. I hope you have a good weekend. And I will plan to see you next week.